Isn't it wild how sometimes the simplest action can have, well, completely unexpected results? Like
Huh.
taking something we know well, say ultra-thin carbon, graphene,
Uh-huh. Incredibly strong stuff.
right? And you stack two layers, you'd think, okay, predictable. But then you just rotate that top layer a tiny bit.
Yeah.
Oh, what is it? Just over 1 degree.
Yeah, about 1.1 degrees. That precise little twist changes everything.
Suddenly it goes from, a normal conductor to maybe an insulator or even a superconductor. It's bizarre.
It really is. And that simple idea, that twist, is the heart of this whole field people are calling twistronics. Twist plus electronics.
So Twistronics is basically studying how that angle between layers, these 2D material layers, fundamentally messes with their electrical properties.
Exactly. And it just exploded onto the scene around 2018, mostly thanks to that work on twisted bilayer graphene, TBG they call it.
That magic angle discovery. Okay, let's dive into that. Why is that specific angle roughly 1.1 degrees so
Yeah.
magical?
Well, when you hit that angle, the electrons inside the graphene layers, they sort of slow down a lot. They stop acting like individuals just whizzing past each other.
And start interacting more.
Precisely. They become strongly correlated. Think of it like instead of billiard balls scattering, they start moving together, almost like a thick liquid or a swarm. It creates this amazing playground.
A playground where you can just tweak the angle slightly or maybe apply a bit of voltage, and the material just flips its identity. Insulator, conductor, superconductor.
That's the power of it. And the superconductivity, while still very cold, like 1.7 Kelvin, is fascinating because of how it happens.
Okay, and that leads to the more recent stuff, right? With 3 layers, MATTG.
Yes, magic angle twisted trilayer graphene. And there, researchers really zoomed in on the superconductivity. They measured something called the superconducting gap.
That's like the energy you need to break the electron pairs apart, a measure of how strong the superconductivity is.
You got it. And in normal, conventional superconductors, that energy gap looks kind of flat if you plot it out.
But that's not what they saw here.
Not at all. They saw a distinct V-shape. Totally different. And that V-shape basically tells us this isn't your standard textbook superconductivity, the kind driven by vibrations in the material's lattice.
So it points to something stranger.
It strongly suggests unconventional superconductivity. The pairing seems to be driven purely by those strong electron interactions we talked about. They describe the pairs as being bound incredibly tightly, almost like little molecules.
Wow. Okay, so understanding that mechanism,
Yeah.
that could be a huge step towards, the dream of higher temperature superconductors.
It's definitely a big clue.
But, doing this kind of science, making these precise structures, that must be incredibly difficult. Which actually brings me to our sponsor.
Ah, right. If you're navigating complex challenges, maybe in the AI space, you should check out Embersilk. They help with AI training, automation, integration, software development.
Yeah, they really dig in to find out where AI agents can provide the most value, whether it's for your business or even just personal projects. You can find them at embersilk.com. Definitely worth a look.
Good resource.
So back to that difficulty. Getting that 1.1 degrees, being off by just 1/10 of a degree apparently ruins the whole effect. How did researchers overcome that hurdle? Making sample after sample sounds impossible.
It was. That was a huge bottleneck. You couldn't just keep making new devices hoping you got the angle right. So the innovation wasn't just the physics, it was the engineering too. They developed this platform, the Mega 2D.
Right, the tiny machine, like fingernail-sized.
That's the one. It's this ingenious little MEMS device that lets them physically twist the layers while they're measuring, so they can dial in the angle, almost like tuning a radio.
So you don't need 1,000 samples, you just need one good one you can adjust.
Exactly. It made exploring twistronics so much faster and easier, a real game changer for the field.
Okay, so with that engineering sorted, where does this lead? What are the big potential applications down the road beyond just understanding fundamental physics?
Well, one obvious area is tailoring electronic properties very precisely. Think about solar cells. If you can engineer the band gap just right using these twists.
You could absorb sunlight much more efficiently.
Potentially, yes. People are talking about pushing solar cell efficiencies maybe even past 50%. That would be huge. And of course, there's quantum computing where controlling these exotic electron states is key.
And I saw something about this idea extending even beyond electrons into light itself. Plasmonic Twistronics.
That's right. It's a newer frontier. They're using similar twisted layer ideas, but to control light at the nanoscale. They've created these complex light patterns, things they call Skyrmion bags, basically intricate topological structures in the light field.
Which could be used for what? Better microscopes?
Super resolution microscopy is one application, yeah. It's about controlling light matter interactions in really sophisticated ways we couldn't before. New kinds of sensors, maybe?
So, the big picture here seems to be we don't necessarily need brand new exotic elements. Sometimes just taking materials we already have and, well, giving them a careful twist unlocks entirely new physics and possibilities.
That's really the core appeal, I think. Having a knob, whether it's voltage or literally rotation angle, that lets you dial in fundamentally different states of matter. Insulator, metal, superconductor. That's incredibly powerful. It's why some see this as a path towards, a kind of holy grail for material science.
Amazing stuff. Well, that's all the time we have for this deep dive. If you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.